Okay guys, so the last few videos we've covered quite a bit of ground, and one of the things that we did cover in a previous theoretical video was the concept of maximum power transfer. Whenever you happen to hook up a load to a circuit, remember there is going to be a certain amount of power that's extracted from that circuit and delivered to the load. However, not all loads are made the same. Some loads will extract a certain amount of power. Some loads will extract less than that. Some will extract more than that. However, there is one unique value for that load that you can hook up to a circuit such that it grabs or gets the max amount of power from that circuit possible, right? And we went through the theory last time. I'm going to use some of those results here in order to work out a particular problem, an example problem. So here, the example that we're going to go through is on maximum power transfer. And the place where I'm going to start is consider the following circuit. Suppose that the circuit that we're looking at contains an independent voltage source providing us with 24 volts. It's hooked up to a resistor here, followed by an independent current source providing us with 4 amps. Then we have another resistor, and then this bottom portion of the circuit is complete. Up here we have a dependent source. It's a current source that provides us with 3 Ix worth of current. Ix has been defined to go down this way. This is an 8 ohm resistor, a 2 ohm resistor, and then lastly, over here, we have a variable resistor R, right? So this resistor has a little dial on it, a knob, that you can actually use to change its resistance value, right? And the question is, what value must R have such that it extracts the maximum amount of power? Whoops, let's clean that up. Maximum from the circuit. And secondly, how much is this power? So it's a two-part question. What value must R have, and so that it gets the max power, and how much is that max power? Now, one of the things that we did previously is we analyzed this problem from the Thevenin equivalent point of view. Remember, max power occurs or is drawn when the value of R is equal to the Thevenin resistance of the entire circuit to the left of the load resistor. And the maximum amount of power itself is the Thevenin voltage squared divided by 4 times the Thevenin resistance. These are results that we had established previously, and they're results that we're going to use. So the question is, more than anything else, if I were to draw, let's say, a box around this entire circuit up here, right? Well, what would the Thevenin equivalent of that circuit happen to be? If we can find the Thevenin voltage and we can find the Thevenin resistance, we can then use these equations in order to find the maximum amount of power, right? Now, we're in luck. I'm not sure if you can see it, but We found the Thevenin equivalent of the circuit inside of the red box in a previous video, right? We used various techniques of circuit analysis to find the open circuit voltage, to find the short circuit current, and then we found the Thevenin resistance based on those. So from a previous video, we found that the Thevenin equivalent of the circuit inside of the box with respect to the terminals A and B, well, the Thevenin voltage was 8 volts and the Thevenin resistance here was 1 ohm. So over here, with respect to the terminals A and B there, that entire portion, complicated circuit in the box, can be replaced with a single voltage source in series with a simple resistor, and those were the values that they had to have. So here, we still have our variable resistor there, like this, right? And according to the theorem that we just stated, max power transfer occurs when the value of this variable resistor has the same value as this Thevenin resistance. So we solved the first part of the problem. So maximum power occurs when this variable resistor has the same resistance as the Thevenin resistance. That happens to be 1 ohm. We used the result in a previous video to establish this. I suggest that you take a look at that video. Right? So we're using previous results in order to continue solving problems that are a little bit more sophisticated. Now, this may seem kind of like cheating, but this is something that's done all of the time in academia. You really need to know how to use other results from other sources to continue along with your work. So this is a good lesson for you to see how it is done as a professor, and it's the type of thing that you can expect to do in your upper division, even graduate and even beyond graduate classes. So using previous results is not cheating as long as you state where your sources are. My source for this solution is from a previous video done in the series. Right. Now, the second part of the question, right, was not just what value must that variable resistor have in order to extract maximum power from the linear network, but what maximum power is. Well, we can use this result found in a previous video. So here, the max amount of power is the Thevenin voltage squared divided by 4 times the Thevenin resistance. Well, the Thevenin voltage is 8 volts. I'm going to square that, divided by 4 times 1 ohm. 8 divided by 4 is 2, times 8 more. This is a total of 16, and the units here is watts. So the max amount of power that can be drawn from this network is 16 watts. If you change that variable resistor to have any other value other than 1 ohm, you're always going to get less than that. Even if you decrease the resistor value or increase it, you can go to half an ohm or 1,000 ohms or 10,000 ohms or anything you want. You're going to get less power than that. Right? Thank you for watching, and we will continue with more examples in further videos. Thank you.